Chapter 7. Failures. We pop A7. The stack is now empty. And we append C7. And we read. Here is the final constraint. Nodes can be taken down, fail and later recover, or crash and stop permanently. Networks can be partitioned, isolating groups of nodes from one another and causing omission faults, the loss of individual messages, as distinct from the failure of an entire node. With this final relaxation, every idealizing assumption has been dropped, and the model reflects the full set of failure modes that a production distributed system must tolerate. Three distinct kinds of failure arrive together, and they are genuinely different problems. A node crashes, it stops, and the other nodes learn about it only through silence. A node crashes and then recovers. Its in-memory state is gone, but its durable state on disk survives and can be replayed. Or the network partitions. Every node is perfectly healthy. They simply cannot reach each other. And now, at last, CAP applies operationally. The partition that we named back in Chapter 4 can finally occur. Everything CAP and PACLC asserted becomes an operational question rather than a theoretical one. There's one fact about this chapter that is harder than any individual mechanism in it, and I want to state it before we go any further. From inside the system, a crashed node, a slow node, and an unreachable node look identical. There is no observation that distinguishes them. Every mechanism in this chapter is designed in the shadow of that fact. Let's establish the vocabulary that makes the rest of the chapter precise. Fault tolerance is the ability of a system to continue functioning correctly even when some machines fail or the network partitions, typically achieved through redundancy. And notice that this is the second motivation for replication, alongside throughput. We could not state it until now, because until now nothing could fail. A liveness property is a guarantee that some specific intended event will eventually occur. For example, a leader will eventually be elected. A safety property is a guarantee that some specific unintended event will never occur. For example, two nodes will never simultaneously believe themselves to be leader. You need both, and it's worth seeing why by imagining each one alone. A system with safety only never elects two leaders because it never elects one at all. Correct and useless. A system with liveness only always elects a leader and sometimes elects two, available and wrong. Keep that pairing in mind because it structures the second half of this chapter. Election algorithms will give us liveness. Only consensus will add the safety. Finally, distributed algorithms are typically designed against one of two assumptions about how a node can fail. Its node failure model. Crash stop. A faulty node may crash at any moment and, once crashed, never resumes execution. A terminal state with no arrow back. Crash recovery. A faulty node may crash at any moment, losing its in-memory state, but may subsequently resume execution typically by replaying durable state from disk. And that recovery is possible precisely because of Chapter 1's write-ahead log. Crash recovery is strictly the harder model to design against, for a reason worth anticipating. A returning node may hold stale beliefs about the world. That is a hazard we will have to address explicitly. Now, given that a node can fail, how do we even find out? Simple failure detectors rely on periodic heartbeats or pings to determine, via silence beyond some fixed timeout, whether a node is alive. The trouble with a fixed timeout is that it forces you to make one choice, once, at design time, for every workload the system will ever run. Choose a short timeout, and you get fast detection along with false positives, where a healthy but slow node is declared dead, triggering a needless failover. Choose a long timeout, and detection is reliable but slow, so the cluster keeps routing requests to a dead node for the whole window. The phi-accrual failure detector improves on that fixed timeout approach with a statistical model. Rather than issuing a binary alive or dead verdict, it computes a continuously varying suspicion level, denoted phi, from the observed timing and frequency distribution of recent heartbeats. As the current silence becomes statistically improbable given past behavior, phi rises. The value of that design is that each application can then choose its own threshold on the same signal. One service may act early and accept some false suspicion, another may wait for near certainty. It allows applications to trade detection speed against false positive rate at runtime, rather than fixing that trade-off in advance. What no detector can do, and this is worth being explicit about, is distinguish a crashed node from an unreachable one. That's why detection provides no safety. Failure detection is inference under uncertainty, and treating its output as fact is precisely how split brain begins. Now let's take the guarantees we built in Chapter 1 for a single node and try to stretch them across nodes that can fail independently. We'll start with atomicity. Guaranteeing atomicity across multiple nodes, that is, ensuring that a transaction either commits on every involved node or aborts on all of them, requires an explicit coordination protocol. The three principal families are two-phase commit, three-phase commit, and quorum-based protocols. Two-phase commit, or 2PC. A designated coordinator, which may also be one of the participants, drives the protocol in two phases. In the voting phase, the coordinator sends the proposed transaction to every participant. Each participant executes its local portion of the work, durably records its readiness, and replies with a yes or no vote. If every participant votes yes, the coordinator proceeds to the commit phase, instructing all participants to commit. If any participant votes no or fails to respond within a timeout, the coordinator instead instructs all participants to abort. Now let's walk the failure cases in increasing order of severity. A participant that fails during the voting phase is treated as having voted no. Everyone aborts. That's safe. A participant that fails during the commit phase is caught up once it recovers, since the coordinator's decision has already been made, and the remaining participants proceed to completion regardless. Also safe. But the critical weakness of 2PC is this: a coordinator failure after the voting phase, but before all commit or abort instructions are delivered, leaves the surviving participants blocked. They are prepared, they are holding locks, and they are unable to safely commit or abort on their own until the coordinator recovers. Availability suffers badly, and it's worth understanding exactly why the participants can't simply decide among themselves. A yes vote is a promise, not a decision. Only the coordinator knows whether everyone said yes. So a participant that voted yes genuinely does not know whether the transaction should commit, and guessing would be unsafe. Three-phase commit, or 3PC, addresses that blocking problem by inserting an additional phase before the final commit. Once every participant has voted to commit, the coordinator broadcasts a pre-commit acknowledgement to all participants before proceeding to the final commit instruction. So any participant that receives this acknowledgement thereby knows that every other participant is prepared and can independently deduce the eventual outcome, even if the coordinator subsequently fails. The inserted phase has exactly one job: to distribute knowledge of the group's readiness before the decision is taken. Combined with per-phase timeouts, this allows participants to safely commit or abort on their own if the coordinator disappears. However, and this is important, 3PC does not fully solve the problem. Its non-blocking property depends on two things: bounded message delay and accurate failure detection. Neither of those holds under a network partition, and a partition can still leave some nodes committing while others abort, producing an inconsistent outcome, which means atomicity itself is violated, the very property the protocol exists to provide. Quorum-based protocols, which we'll discuss under consensus shortly, are generally required to close this remaining gap. The pattern to carry forward is this: blocking but simple coordination versus non-blocking but complex coordination, and neither one is partition safe without a quorum. That's atomicity. Now isolation. Distributed locking, commonly implemented via leases, which are locks that automatically expire after a timeout, extends Chapter 1's pessimistic concurrency control across nodes. The automatic expiry is what makes a lease safe against a holder that has crashed and will never release it. But the same expiry introduces a safety risk that single node locks never had. A process may believe it still holds a lease that has, in fact, already expired, for instance, due to a long garbage collection pause or a network delay, and it may then act on that stale authority. Look closely at the timeline, because the subtlety is precise. The lease expiring is an event that happens on clock. It is not a message delivered to the holder. A paused process has no way to observe that time passed while it was stopped. So it wakes up and writes, believing it is still the sole authority, while a second node has legitimately acquired the lease and is writing too. Two writers on a resource that permits one is a safety violation. It is exactly the anomaly that Chapter 1's locks existed to prevent, reintroduced by the network. Fencing tokens address this. Each lease acquisition is issued a monotonically increasing token, and any resource protected by the lease rejects operations tagged with an older token than one it has already seen, safely blocking a node whose lease has silently expired and notifying it once the expiry is detected. Notice where the decision moved. We stopped trusting the participants' belief about the clock, and we made the resource the arbiter. And all the resource has to do is compare two integers, remembering the highest token it has seen. No clocks, no trust, no negotiation. Monotonicity is the whole mechanism, the same device we saw as monotonic transaction identifiers in Chapter 6, used here for authority rather than for ordering. And that gives it a property we should appreciate given where we are in the course. Correctness no longer depends on any node's belief about the clock, which is exactly the right property to have under C6. Now, what happens to our replication schemes when a replica actually fails? The implications differ depending on the scheme in use. Let's start with leaderless replication. Hinted handoff, used together with sloppy quorums, allows a write to succeed even when one of its target replicas is temporarily unreachable. The coordinator stores the write as a hint on another healthy node and replays it to the intended target once that node recovers. The quorum is called sloppy because the set of nodes that acknowledge the write is not the intended replica set for that key. So a later read quorum drawn from the intended set may miss the write entirely. This creates a temporary weakening of the W plus R greater than N guarantee for improved write availability during partial outages. And there's a residual risk that we need to name because we'll return to it at the end of the chapter. If the node holding the hint is lost permanently before the handoff completes, the write it was holding is lost with it. Anti-entropy and red repair can reduce that risk, but they cannot eliminate it. Now, leader-based replication, where two very different problems wear the same word, recovery. Replica or follower, recovery is the easy case, because the log already holds the answer. When a follower fails and later recovers, its write-ahead log identifies the last transaction it had durably applied. The leader then streams every subsequent update to bring it back in sync. That's pure catch-up. There is nothing to decide. And it's identical in shape to bootstrapping a brand new replica from Chapter 4, which makes this the write-ahead log's fourth and final appearance in this course. Leader failover is the hard case, because it requires a decision that the whole cluster must agree on. The failure of the leader itself requires a re-election, and it proceeds in 3 steps. First, the failure must be detected, typically via heartbeats or pings. Second, the best available candidate must be selected, ideally the most up-to-date remaining replica. And third, the cluster must be reconfigured to recognize the new leader. This process must be handled carefully to avoid data loss, particularly when the newly elected leader has not yet replicated every write that the old leader had accepted before failing. Look at the 2 logs on screen. The writes at the tail of the old leader's log were acknowledged to the client, and they exist nowhere else. Failover has to bound that loss deliberately, not assume it away. So, recovering a follower is bookkeeping. Replacing a leader is a decision. Let's look at how that decision gets made. Because many distributed algorithms are simpler to reason about with a single coordinating node, leader or coordinator, election is a recurring building block. A correct election protocol must maintain the liveness property that a leader is active for most of the system's operating time. And it must also guard against the split brain problem, in which a partition or a botched election leaves 2 nodes simultaneously believing themselves to be leader. That is a safety violation, and it can lead to directly conflicting operations. Here are the principal leader election algorithms. The Bully algorithm. Nodes are assigned unique, totally ordered ranks. On detecting a leader failure, a node initiates an election. Higher ranked nodes bully lower ranked ones out of contention, and the highest ranked surviving node becomes leader. Next in line failover. The current leader maintains an explicit, pre-agreed list of backup nodes in priority order. On failure, the highest ranked available node on that list is promoted directly, avoiding the overhead of a full election. Candidate and ordinary nodes. Nodes are divided into 2 roles. Ordinary nodes are responsible for initiating an election among candidate nodes, and the highest ranked active candidate wins, with an explicit tie-breaking rule for elections that start simultaneously. The invitation algorithm. Every node begins as the leader of its own single node group and invites other nodes to join. Groups merge whenever 2 group leaders discover and connect to each other, eventually converging on a single group with a single leader. And the ring algorithm. Nodes are arranged in a logical ring. An election message circulates around the ring, and the highest ranked node encountered during a full traversal is elected leader. All 5 of these are effective at initiating a new election during failover. That is a liveness property, and every one of them delivers it. But none of them on their own guarantees the safety property needed to prevent split brain during network partitions. And the picture on screen shows exactly why. Hi, a partition can leave two sides of the cluster each electing their own leader independently, because neither side can see the other, and from the inside, each side's election is textbook correct. Note as well that neither side is even a majority of the cluster. Nothing in a ranking scheme requires one. The consequence is two authorities accepting rights to the same data, with directly conflicting operations and no record of their relative order. Electing a leader is easy. Guaranteeing that there is at most one is the actual problem, and it needs a majority, not a ranking. Achieving that stronger safety guarantee requires consensus. Consensus is the process by which multiple processes in a distributed system agree on a single value. Consensus is trivial under ideal conditions, with no network delay, no node failures, and no partitions. But real systems must solve it under exactly the conditions those idealizations exclude, which is what makes consensus one of the most consequential problems in distributed systems. A correct consensus algorithm must satisfy three properties. Agreement. No two correct, non-faulty processes decide on different values. Validity. The value that is decided must have been proposed by one of the participating processes, ruling out trivial solutions that simply hard code an answer. And termination. Every correct process eventually reaches a decision. Remember those three. We're going to come back to them shortly in a rather uncomfortable context. Paxos structures consensus around three roles. Proposals receive values from clients and put forward proposals. Acceptors vote on proposals. And learners record the outcome of accepted proposals. A proposal is only accepted once a quorum of acceptors has voted for it. Each proposal carries a proposal number, conventionally a combination of a monotonic counter and the proposing node's identifier, used to establish a total order over proposals and to resolve conflicts between competing ones. Despite its reputation for complexity, what Paxos guarantees is clear enough. It guarantees safety, that is, agreement, even in the presence of node failures and an unreliable network, through this quorum-based voting and replication process. Liveness, that is, termination, is not guaranteed in the fully general asynchronous case, which is a consequence of the FLP impossibility result we'll discuss shortly. But it is readily achieved in practice with reasonable timeouts. Raft was designed explicitly to be easier to understand and implement than Paxos, while providing equivalent guarantees. Each node is at all times in one of three states: leader, follower, or candidate, and the protocol proceeds through two largely independent subprotocols: leader election and log replication. For election, all nodes start as followers. A follower that stops receiving heartbeats from a leader transitions to candidate and starts an election, becoming leader if it wins a majority of votes, or reverting to follower otherwise. For log replication, once elected, the leader is solely responsible for handling client requests. It appends each request to its own log and replicates that log entry to its followers. Once a majority of the cluster has acknowledged the entry, the leader commits it and consensus on that entry is achieved. A lagging follower catches up later without blocking anything. And there's the answer to split brain sitting in one word: majority. A Raft leader needs a majority of votes, and the minority side of a partition simply cannot assemble one. That's not cleverness, it's arithmetic. Which means consensus has effectively rebuilt the single ordering point that made single leader replication strong in Chapter 4, this time safely. Now let's generalize from agreeing on a value to agreeing on an order. Broadcast protocols disseminate a message from one process to a group, and they are the basic building block underlying both database replication and higher-level distributed coordination. Three broadcast orderings are commonly distinguished, and each one adds a guarantee the previous one does not make. FIFO broadcast guarantees that messages originating from any single process are delivered to every recipient in the order that process sent them, though messages from different senders may still interleave arbitrarily. Causal broadcast guarantees that causally related messages, regardless of sender, are delivered in an order consistent with their causal dependencies. That's Chapter 6, happened before relation applied to messaging. Total order broadcast, also called atomic broadcast, guarantees that every recipient delivers every message in the same sequence. It combines three things: reliable delivery, atomicity, meaning a message is delivered to all correct processes, or to none, and a single total order. Because achieving that in the presence of failures requires detecting and working around coordinated failures, it is typically implemented using failure detectors and fallback election mechanisms, which is to say, using the machinery from earlier in this chapter. Two related notes. Virtual synchrony is a related technique for delivering messages consistently to a dynamically changing group of recipients. And total order broadcast can itself be framed as an instance of the consensus problem, with agreement here meaning agreement on the relative order of messages rather than on a single value. Those are two views of the same problem. Zookeeper Atomic Broadcast, or ZAB, is a leader-based atomic broadcast protocol originally developed for a widely used coordination service system that provides both leader election and consensus on the ordering of write operations. It proceeds through three phases within each epoch. First, discovery, in which a prospective leader proposes a new epoch to the other nodes. Second, synchronization, in which the elected leader synchronizes every follower's state by delivering any proposals from earlier epochs that the follower may be missing. And third, broadcast, in which the leader accepts client requests, establishes their order, and broadcasts them to the followers. And now we can say what all that ordering machinery is ultimately for. State machine replication, or SMR, models each replica as a deterministic state machine, with all replicas initialized to an identical starting state. As long as every replica applies exactly the same sequence of client requests in exactly the same order, the replicas remain identical. That provides fault tolerance, since any individual replica may fail independently without the service as a whole becoming unavailable or inconsistent. And note what is absent from that design. There is no reconciliation step because none is needed. Identical inputs in identical order produce identical state. SMR therefore relies directly on a total order broadcast protocol to guarantee that every replica agrees on the request sequence, which is what ultimately guarantees the replicated state machine's correctness. Look back at chapter 4 with this in hand. We described replication there without ever saying what ordering guarantee it assumed. This is the one it assumed. Before we finish the chapter's mechanisms, we need to confront two results that tell us what cannot be achieved, because they explain why every protocol we've just described makes the compromises it makes. The two generals problem is a classical thought experiment demonstrating that two parties communicating over a channel with possible message loss cannot reach mutual common knowledge of an agreed decision using a finite number of messages. And by extension, no protocol built purely on unreliable message exchange can guarantee agreement with absolute certainty. Follow the regress on the diagram, because it's the whole argument. The first general sends the plan, but did it arrive? The second acknowledges, but did the acknowledgement arrive? The first acknowledges the acknowledgement. Every message adds one more level of I know that you know that I know. None of them closes the loop. The second result is FLP impossibility, due to Fisher, Lynch, and Patterson. It states that in a fully asynchronous system, one with no bound on message delay, no deterministic algorithm can guarantee agreement, validity, and termination simultaneously if even a single process may crash. There are those three properties again. And FLP tells us we may have any two of them. Every consensus protocol in this chapter gives up the same one, termination. In practice, real consensus protocols such as Paxos and Raft sidestep this impossibility in two ways. They rely on partial synchrony, meaning message delay is bounded but unknown in the common case. And they rely on timeouts, a failure detector that is allowed to be wrong and then corrected. Together, these sacrifice guaranteed termination in the worst case in exchange for termination that holds with overwhelming likelihood in practice. I want to be clear about the status of these two results because it's easy to file them away as academic. They are not engineering limitations that a bigger cluster or a better network eventually closes. Every practical solution in this chapter consciously trades away an idealized guarantee, and a competent design says out loud which one it traded. One more mechanism, and it addresses recovery after the fact. The distributed snapshot problem addresses how a system can capture and later restore a consistent record of its global state as it existed at some point before a failure. The central difficulty is one we inherited from chapter 6 rather than this one. As established there, no node has direct access to any other node's motion of the same instant. So nodes must coordinate explicitly to record both their individual local states and the state of the communication channels between them together in a way that yields a globally consistent picture. Look at the two candidate cuts on the diagram. because the definition of correctness is visible in the difference between them. The first cut places a message's receipt inside the snapshot while leaving it sent outside, an effect recorded with no cause. No execution ever passed through that state, so nothing could ever be restored to it. The second cut is consistent. Every recorded receipt has its send recorded too, and the message crossing that cut forward is still in flight, which is exactly why the channel's contents have to be saved alongside the local states, or it vanishes. Formally, a captured snapshot is considered consistent if it corresponds to a state the system could actually have passed through, reachable from the state at the start of the snapshot procedure, and capable of reaching the state at its end. The Chandy-Lamport algorithm is the standard technique for capturing such a consistent global snapshot in an asynchronous distributed system, without halting the system during the process. So there is no global now to photograph. A consistent snapshot is not a moment, it's a plausible moment, assembled from local states plus the messages between them. Finally, let's revisit replication and consistency one last time under the complete constraint set. Unquote. Revisiting replication. One of the central motivations for replication, beyond throughput, is fault tolerance itself, a claim we could not make until this chapter. Single leader replication, despite its simplicity, introduces a single point of failure. If the leader fails, write availability is compromised until failover completes. Multi-leader, or equivalently, multi-primary replication mitigates this by distributing both load and leadership responsibility across multiple nodes, often placed in physically distinct data centers, so that the nodes fail largely independently of one another. That improves overall system reliability. Revisiting consistency models. Now we reanalyze the achievable consistency models across all replication schemes under the complete set of real-world constraints C1 through C7. Under active failure scenarios and network partitions, achieving strong guarantees such as linearizability becomes substantially harder. Doing so now generally requires the consensus protocols and total order broadcast mechanisms developed in this chapter, since maintaining a single globally agreed sequence of operations in the presence of failures is precisely the consensus problem. Outside of active failure scenarios, the consistency results established in earlier chapters remain unchanged. And there's one more revision, which closes a loop we opened earlier in this chapter. Eventual consistency's own convergence promise is conditional in two ways that are easy to forget. It applies only to replicas that remain reachable, and it applies only once a write has reached a durable quorum, since a write held only as a hint on a node that is then lost permanently has nothing left to converge to. Step back and look at what just happened across this chapter. In chapter 4, single leader replication gave us linearizability for free, simply by having a leader. It was never free. It was borrowed against A7, and this chapter is the bill. Let me summarize chapter 7. Every mechanism developed in chapters 1 through 6 was analyzed under A7's convenient fiction that nodes and networks simply do not fail. Constraint C7 removes that fiction and, in doing so, forces every one of those earlier mechanisms to be re-examined for what happens when a participant crashes, partially recovers, or becomes unreachable mid-operation. The problems this creates are correspondingly broad. Failures must first be detected, without perfect information. The atomicity and isolation guarantees built for a single node in Chapter 1 must be extended across nodes that can now fail independently mid-transaction. The single-leader architectures of Chapter 4 need a way to replace a failed leader without ever allowing two nodes to believe themselves leaders simultaneously. And most fundamentally, this chapter's theoretical results establish that no protocol can guarantee agreement with certainty over an unreliable channel per the two generals problem, or guarantee termination deterministically in a fully asynchronous system with even one faulty process per FLP impossibility, which means every practical solution must consciously trade away some idealized guarantee. The chapter's mechanisms address these problems in a clear hierarchy. Probabilistic failure detectors replace naive fixed timeouts with a tunable trade-off between detection speed and false suspicion. 2 and 3-phase commit extend Chapter 1's atomicity across nodes, with 3 PCs extra phase and quorum-based protocols narrowing, though not eliminating, 2 PCs coordinator blocking weakness. Fencing tokens extend Chapter 1's isolation guarantees safely across leases that can silently expire. Hinted handoff and leader or replica failover extend Chapter 4's replication architectures to survive real node loss. And because leader election algorithms alone provide liveness, but not the safety needed to prevent split brain, consensus protocols such as Paxos and Raft, together with the total order broadcast and state machine replication techniques built on top of them, are what ultimately let a replicated system remain both safe and available under real failures. With the Chandy-Lamport algorithm extending Chapter 6's causal ordering machinery to let the system recover a globally consistent checkpoint after the fact. The trade-offs here are correspondingly sharper than in earlier chapters. Blocking but simple coordination versus non-blocking but complex coordination. Strict quorum correctness versus availability during a partition as traded by sloppy quorums. And per FLP guaranteed safety versus guaranteed termination, which every practical protocol resolves by sacrificing termination guarantees in the worst case in exchange for termination that holds overwhelmingly often via partial synchrony and timeouts. As a matter of practical guidance, lightweight heartbeat-based detection and simple failover are adequate wherever brief post-failure inconsistency is tolerable. Two-phase commit remains defensible for tightly coupled, low-latency, well-managed internal systems, while loosely coupled or large-scale systems increasingly avoid distributed transactions altogether, in favor of asynchronous, idempotent workflows. And full consensus protocols, Raft in particular, given its comparative simplicity, are the appropriate and often unavoidable choice for any component whose correctness depends on a single, safely agreed leader or state, such as coordination services, distributed locks, and metadata stores. Even though they carry the highest implementation and operational cost of any mechanism in this chapter. Notice the shape of that guidance. Consensus is unavoidable for a narrow set of components and overkill for everything else. C7 did not really add new mechanisms so much as force every early one to answer a new question: what happens if a participant disappears mid-operation?